Welcome back. We're in momentum here on worksheet 2, number 3. A handball of mass 45 grams strikes a hard wall perpendicular with a initial speed of 46 meters per second. The handball is in contact with the wall for 0.078 seconds and then rebounds straight back with a speed of 39 meters per second. What average force was applied to the handball by the wall? And hint, use impulse and momentum to solve. All right, first we're going to draw two pictures here. I'll define my action here. It is striking this hard wall perpendicular here. And so we are looking both before and after this action here. I also make some other things here, make some other notes to myself. The 45 grams. I go, hey, that's not in SI units. I immediately convert that to kilograms, so I divide them by 1,000, and so we get 0.045 kilograms. Okay, cool. The other ones are in SI units there. So we'll make a wall here. And the little angled slashes coming out of anything mean that it's an immovable surface. It's something that's not like breaking or generally moving or anything. So ground usually is, and many times walls are. We'll have a handball come in here, and so let's say, well, let's do it right before and after the strike. So just before it strikes here, it's got a velocity going in there at 46 meters per second. And then it's coming in contact and then rebounds straight back. So then afterwards here, well, let's see if I can just copy all this. Make that a little bit faster for you. Cool. And so then right afterwards here, the thing is coming back out here with a speed of 39 meters per second. And if you needed to, I'll go ahead and copy that one more time. And I could draw while it's actually hitting here. Just want to do that just so we can have a nice little discussion here. The ball, oh gosh, the ball is going to be a little bit deformed here. So let's see if I can just draw an oval instead. Yep. And then things are going to get forces here. The ball is going to be hitting the wall, and the wall is going to feel a force going that way, and that would be like a normal force. And the ball is going to feel a normal force going that way. How do these compare? It's right, they are the same. Newton's third law. Ball hits wall, wall must hit ball. The exact same amount of force. Okay, cool. So that's happening, and I can go ahead and put the time in there of 0.078 seconds. Great. So what was the average force applied to the handball? All right, well, first let's go ahead and let's define our system here. And my system is probably just going to be the ball in this case. Notice I'm not going to include the wall. The wall's not really moving, we would generally say, because it's attached to the ground. But wait, it's got to be transferring. If it's changing its momentum, it's got to be transferring that momentum like somewhere, somehow. What's going on? Well, the wall is attached to the earth, so the wall and the earth is actually one thing that's then going to be like moving together. So ball hits the wall, ball was going to the right, now the ball is going to the left. And so then the wall and the earth is actually going to be moving to the right there. But let's go ahead and let's just make the system the ball, since that's usually a little bit easier in a case like this here. Let's go ahead and let's look at the change in momentum of that ball. I know that there's going to be a change in momentum because we had momentum coming in here, and then afterwards we have momentum coming out there. And so that means that let's do it vectorially here. The change in momentum is just the ending bit minus the beginning bit. Let me show that vectorially here. The beginning bit was momentum that was going this way. The ending bit is momentum that's going that way, and we're going to subtract those two. And you go, oh, well now if I subtract those two, they're not even going the same direction. We're looking for the difference between these. Well, the difference between these is going to be like, well, that's going to be like if I had one of the rightmost arrow, the right arrow that way, oops, and the left arrow that way, and I'm looking for the difference between them, that's like from here to here. That's a really big difference. That's a bigger difference than if I had one of those. Let's say if I flipped the left arrow around. If I flip that left arrow around, and let's say that it's smaller because it's not going as fast afterwards here, right? The difference there would be less. The difference here would be just from here to here. Okay, so the fact that it's going the other direction shows that it's actually going to be a bigger change of momentum, right? You had to not only slow this thing down to 0, but then you had to speed it up going the other direction there as well. Okay, cool. All right, so that's, sometimes I think about that vectorially there as well. Let's go ahead and let's do it numerically though. So the ending momentum, we know it's just the mass of this ball times the ending velocity times the mass times the beginning velocity. Oh, notice I can use some algebra tricks here to make this a little bit simpler. I see that mass is common in both of these, so it's m times the ending velocity minus the beginning velocity, and I might also recognize that that's just mass times the change in velocity there. Okay, cool. We go and we look at we know the ending bit, which is 39, and it was going to the left, and the beginning bit was it 40? What? 46. So let's go ahead and I'm going to even write that out there. So the end was 39 minus the beginning, which was 46. Now, when I go and do that, notice that that's just a difference of 7 there. It would be -7 in that case. When I go and do it like that, did I just find this difference, or did I find this difference? You're correct. I found just this difference if I write it like this. Yeah, because the difference was just the 39 plus the 40 minus the 46, so that you just find the difference between 39 and 46. But this 39 and 46 is a little bit different than that because one of them is going this way to the left, and the other one's going this way to the right there. So I need to be able to show that numerically as well. What did we forget? That's right. The 39 was the one going to the left there, and things going to the left we generally say are negative, right, to be able to numerically show that this is going the opposite direction than this other one. So this is the -39, and this one was the +46 there. And we're looking at, these are the velocity vectors there, even though in this case they're actually momentum vectors, so maybe I shouldn't write that there because that could be really confusing. Okay, so the velocity going backwards, only because my picture here was, I drew it going to the left. I could have flipped this picture around and then I would have -46 coming in and +39 coming out if I had had the ball coming in from the right-hand side. But it doesn't matter because you'll always get one of them to be negative and the other positive. And so now when I go and do that, I gotta pick up my calculator for that one. 39 minus 46. So you get 85 as a difference there. And 85 times that mass there of 0.045 gives us 3.825. And that's negative in this case, -3.825 meters per, hold on. It's not just meters per second, it's meters per second when we do the change in velocity there, but times the kilograms, so now it's going to be kilograms meters per second. So I'm always like trying to double check myself as I go along there. So, I always make mistakes as I go along, and hopefully I catch those as I go along then too. So then this is the change in momentum. Why is it negative? Well, let's think about this. We just changed from the positive momentum going to the right there, and then we had to flip that all the way around going to the left there. So the change in momentum is this guy right here. This arrow represents the change in momentum from the 1 bit all the way to the beginning to the other bit. So you could say from the beginning bit all the way to the end bit there, right? And that's literally what we're doing. Because this one to the right there was the end bit, and the one to the left there was the beginning bit. So that's why I'm drawing it that way. Okay, so and this arrow, this change of momentum, is going to the left there, which means that it would be a negative. So that vectorially this matches up with our numerical bits there. That's why it's negative. It had a change that was going to the left. All right, so then what are we trying to find here? We're trying to find what average force was applied to the handball. Well, we found some change in momentum, and then I go back to my notes there, and I recognize that the change of momentum is also equal to the force that's applied over some time. And so now I can go and plug that in there and go, okay, so some force is going to be applied from the wall or on the ball by the wall, and it'll take some time that force will be applied over, and that's going to be equal to my negative 3.825 kilograms meters per second. Now I know the time because it told me the time there, so I'm going to go ahead and I'm going to plug in the time there with 0.078 seconds. I remember writing that one. And now I can just go and solve for the force here because I have everything else. So I take my previous answer and divide it by 0.078 there, and I get negative 49.04 newtons. I would expect that since I have all SI units here, and I can go and look that I get kilograms meter per second, divide by another seconds, that's kilograms meters per second squared, and I think to myself, oh gosh, that's bad, and I think to myself, hey, the sum of the forces is equal to mass times acceleration, and newtons I expect to be equal to kilograms times the meters per second squared. Oh, that's right, so that actually gives me second per seconds, then divided by another seconds, that's per second squared then, which is Newton. Great. Now it's negative. Why is it negative? Well, what force is causing this change in momentum? We look back at a picture here and go, oh, that's the force that's on the ball by the wall there, and it's going to the left, which is negative. Oh, cool. Sweet. So when we're consistent with our signage here, things come out just right here. You notice down here that for the answer there, I gave you just the size of that. I only gave you the magnitude, but it's actually going to the left there. Okay, cool. Great. That's it. Have a beautiful day. See you.